Hi, and welcome back to Allen High School's discussion of bonding at the pre-AP 10th grade honors level chemistry. Now, we're going to just finish up one last example and do a summary chart. So we want to compare dominant types of intermolecular forces and then rank them based on melting and boiling points. So the first step is to classify. So H2S is non-metal, so it's covalent. CH4 is non-metal, it's covalent. LIBR is metal, non-metal, so it is ionic. We have a non-metal, it's covalent. Non-metal, it's covalent. Now, ionic doesn't have a dominant. It's not really technically an intermolecular force. I don't really like calling that. We're actually breaking a bond. And that takes a ton of energy. Full positive cation, full negative anion, and we're breaking that bond that requires a lot of energy, so that's going to have the highest melting point. Now, in order to classify these others, we have to decide if they're polar or nonpolar. If you did the Lewis dot, and I'm now assuming you can do that, this has an AB2X2 structure. This is AB4. This is AB3X. And this is AB4. So let's compare those. This is got non-bonded pairs. So this is a polar, I didn't want to use that color. This is a polar molecule. Now, once you've decided if it's polar, you want to ask yourself, can it hydrogen bond? Do I have an H to an S, or excuse me, H to an F, H to an F, H to an O, and it may be to another atom, or H to an N, and that could actually be to two other atoms. And in our case, the answer is no. So our dominant intermolecular force is dipole-dipole. They all have that little bit of London dispersion underneath. Okay? This next one, we have a covalent. I have the exact same atom all around the center. So this is a non-polar molecule. So the only thing that's available is London dispersion. I have a non-bonded pair of electrons here. At the pre-AP level, that automatically means that it's a polar molecule. Now, once you get to AP, we'll see some other examples where that's not true. But the key here is we don't have the identical thing all around the central atom. It's polar, so ask yourself, can it hydrogen bond? And that means, do we have H to an F, H to an O, H to an N? And the answer in this case is yes. So hydrogen bonding is the dominant force with that always underlying London dispersion. This time I have a carbon. I have the exact same atom all around it. So this is non-polar covalent. The only thing available to it is London dispersion. Now, assuming similar sizes, and at your level, that's really what we will be doing, so you don't really need to worry about that too much. We're not going to get into too tricky of ones for you yet. Okay? Hydrogen bonding is going to be stronger and take more energy. So hydrogen bonding is stronger, so it's going to take more energy to melt than dipole-dipole. So that would be 3. Now, we have 2 London dispersions that we need to compare. And to compare the London dispersions, we look at the size. As you increase size, so the bromine is a much bigger atom than the hydrogen is. As you increase size, you increase electron density, you will increase your London dispersion. So bigger one wins. So that means this one is going to be stronger and this one will be weaker. Okay? So that's how you would rank them. You'll get some practice in class on that. Now, I want to just clean this up with filling in this bond comparison, and I will do my very, very best to remember to post the teacher version of this. But for now, I want to fill in at least a brief outline to help you with your quiz, because you do have a quiz next class. So we have an ionic bond. Our general formula is going to be a metal and a non-metal. I'm not sure what she meant by structure. Ms. Marusik put this together, and it's an awesome chart. I just don't remember what she meant by structure. So we're going to stick with this. This is non-metal with non-metal. And then this is also non-metal with non-metal. But let me show you a way we can depict a comparison of these. Okay. Ionic is a full positive attracted to a full negative. When we're talking about polar covalent, it's a partial positive and a partial negative. And when we're talking about nonpolar covalent bonds, there's no polarity. There's none. So there's no pull. It would be a 0 and a 0. I don't know how to write it. There's no pull of electrons. The difference in electronegativity here is greater than or equal to, I did that backwards. So the difference in electronegativity is going to be greater than or equal to 1.7. For a polar covalent, it's going to be greater than or equal to 0.3, but less than 1.7. And here, it's going to be less than 0.3. These are usually called compounds. These are typically called molecules. How do elements reach that stable octet? Well, with covalent, they pair share. You can think of that. They share pairs of electrons, so we put them around in pairs. Here, the metal is going to donate an electron to become a cation. Remember, the cation is positive, and the other will accept electrons to become an anion, and the anions, remember, are the negative ones. And metals tend to be your cations, and nonmetals your anions. How do we do their Lewis dot structures? Well, for ionics, we're going to use brackets and charges. And remember, you just have to order them so that negatives and positives don't touch one another. We're not getting into crystal structures. We don't have to worry about that. So just make sure they alternate positive and negatives. For polar covalent and nonpolar, you'll have central atoms with either atoms or non-bonded pairs. Okay? So I'll just put another C there. Okay? So this would be for molecules now. I don't like the bond there. Let's call that a molecule now. Okay? Molecule. Basic properties. These conduct electricity. If they're melted or molten state, or if they're dissolved in an aqueous solution. Okay. Here, these do not conduct ever. They do not ever conduct electricity. All right. These dissolve in polar solvents. These dissolve in non-polar solvents. And strength and melting point would go in this direction, assuming same size. And boiling point would all go in that direction. These tend to be the weakest, and these are definitely the strongest, regardless of size. Okay? So hopefully that gives you a good overview for your quiz. So until I see you again in class, this is signing off.